In this video, we'll learn about weak bases and the weak base equilibrium constant Kb. And what makes a weak base as opposed to a strong base is it undergoes less than 100% ionization or dissociation. And so we describe this using the Kb reaction. And in the Kb reaction, what we have is the base, which we typically just represent as a B. And so whereas the acid was an HA because it can donate a proton, a base can receive a proton, so we just write B here. It is going to react with water, so we're considering only aqueous solutions here. And whereas the acid would give a proton to water, water will give the proton to the base. Or if you prefer, the base will abstract or take a proton from water. All right, so what's this going to generate? Well, the base is now going to pick up a proton, so it's going to be BH. It's going to have a positive charge. The water has lost a proton, so it has only got one hydrogen now instead of two, and we recognize this as the hydroxide ion, or OH-. We could write it HO- if you really wanted to, but for whatever reason, we prefer to write it like so. So that is the ion that is responsible for raising the pH. It has a bitter flavor, like all bases do. It's an equilibrium, so we've got an equilibrium constant, so we can write K for the equilibrium constant, and B to remind us it is a base, and it is then the equilibrium concentration of products divided by the equilibrium concentration of reactants. And because water is a pure liquid, it has an effective concentration of 1, and so we could write the number 1 here, but of course that will not change the equilibrium itself. The equilibrium constant, the higher it is, the stronger the base is. So if Kb is large, it is a strong base. Actually, I should say it is a strong weak base, and if Kb is small, then it is a weak base. So strong bases don't have a value of Kb, or a Kb is so large it's impossible to measure, but weak bases have equilibrium constants that can be large or small depending on how strong or weak the base is. So let's have a look at an equilibrium constant table. So here's a table from our textbook of some common weak bases. So here's the carbonate ion, and it's got a weak base constant of 10 to the minus 4. So for a weak base, it's pretty strong, actually. Methylamine here, again, 4.4 times 10 to the minus 4. So it's a little bit stronger of a weak base than carbonate, and so on. Ethylamine, 5.6 times 10 to the minus 4. As we go down the list, our bases become weaker. So ammonia is 10 to the minus 5, bicarbonate 10 to the minus 8, aniline 10 to the minus 10. So these are weaker weak bases, and these are stronger weak bases. And again, look at all these reactions. The thing is reacting with water, and the water is giving a proton to the base. So it's protonating the base, and the base is initially neutral. It's converting it into a cation every time. In this case here, the base is -1, so when it protonates, it forms the neutral carbonic acid compound. But again, these are all bases because they are producing this hydroxide ion. And remember, the Arrhenius definition we met earlier was essentially bases are anything that can raise this concentration in water. We'll see that this raises the pH and lowers the pOH as well.